Thor, word is yours. Thank you so much. Yeah, can you hear me well? Is it working? Yeah, perfect. So my name is Andrejs Krauklis, and I'm an associate professor at Latvia University of Life Science and Technologies. And there are a bit of an echo. No worries at all. So yeah, and basically, so what I'm going to talk about today is the hydrothermal aging and degradation of polymers and polymer composites in relation to that, and how do we model this using physical methodologies, so physical modeling and multi-scale modeling approaches, and then without further ado, let's look into the uh, technology that we have to offer here. So let's start with the big picture. So the introduction is that, let's say, polymers are everywhere in our modern life. So they're also environmentally, they can be exposed to water and humid air environments, especially in our climate. It's also the temperatures and let's say the cold and so on. So there are really a lot of issues that come with the environment. And we are also looking into the aging of polymers with the effect of temperature and the effect of, let's say, humidity, the presence of water, the acidity, and so on. So all the environmental factors that can be there and affect the material. Looking at different polymers can be quite different from one to other, and we'll explain in which sense that is and how that can come into hand when analyzing the behavior. And also that means, however, that while the materials can differ, it means that the aging mechanisms can differ also quite severely. So all of that has to be assessed individually. And in case of polymer composites, it's not only the polymer, but it also is a reinforcement material, which is typically, let's say, if we're talking fiber reinforced polymer composites, that can be a glass fiber or a carbon fiber, or more recently, natural fibers and basalt. And also there's the third part, the secret ingredient, the sizing of the fibers, and then therefore also the sizing rich interface, which can also affect the aging of other constituents. So let's take a look how we can, let's say, work with this very complex interaction. And let's say, to break down this complex, let's say, process of aging and all underlying processes, we try to build a multi-scale modular approach. So to break down a very complex issue into smaller pieces and to try to analyze mechanistically how each of them is working. So let's look into molecular mechanisms, kinetics, and interconnectedness of the constituents. But also, why do we need that? So in the modern times, let's say, it's especially important to understand the lifetime of a material. So how long does a material survive and can be put into use? For example, we're looking into towers like wind turbine towers. That is something which currently is an issue in Europe in a way that with the recycling, because in real life, these turbines can live much longer than they're actually commissioned before. So because we are over, let's say, we don't want to risk anything. That's very smart, but that means that also we lose 10 years of real use of a turbine, for example, in the practice conditions. And the problem at the moment is also what to do with the with the material that is waste, because composite recycling technology is still being developed very, very eagerly, but there are a lot of problems still. So lifetime. So now, as you know, life cycle assessments, that's a hot word, life cycle assessment and cost analysis, LCA, LCC. And we want to have a method reliably to predict the lifetime of polymers and polymer composite materials. And in order to do so, we propose the development and advancement of the modular modeling framework, which is presented here. And also we look into one case example, which is so I'll go a bit into more detail. QSPR methodology that we developed to looking in the case of a PLA polymer, environmental agent of that. So lifetime prediction. As I said, the process is very complex and can be broken down. So the interaction between the polymer and the environment can be broken down into many smaller parts and parameters. So environmental factors, temperature, moisture, pH, mechanical loads. There's a lot of inherent processes, physical aging, hydrolysis for some, post-curing, internal stress relaxation. And we have to look also on different scales. So it is something happening on the molecular scale, the micro. Then it is the engineering properties that being affected, the macro properties that we're looking, and then there's the bridge connecting it all together, the mesoscale. So also, in some cases, we want the material to degrade. So for example, if this is something bio, like a compostable material, so we also have to know the composition criteria in that case. So we have to look at the two-edged sword. So in some cases, structural materials, wind turbines, we want them to stay healthy as long as they want, or as they can. So it's a safety criteria we take into account in the modeling. We have biodegradable, biocompostable cups or something which have liner made of polymer. We want it to be able to degrade it fairly quickly. So that's a favorable decomposition criteria. Now, let's take a look closely into the composite polymer composites. So we have three constituents matrix, the polymer, respectively, reinforcement, that's a fiber, and the interface region. And then when each of these components is intact, in contact with the environment, there's plenty of various sub-processes which go on. So let's start. Mostly we concentrate on the polymers today. So I will talk about the processes which work and affect the polymer. And also a bit of, I will show the interconnectedness with the other modules, but let's look into that in more detail. First of all, let's say we look environmental issue. We have a polymer which is immersed in water, or we have a rain, let's say wind turbine standing there and the rain is dripping and affecting the polymer matrix. So water starts to diffuse into the polymer. Initially we have, let's say, a dry state. Although here we have a true water content, so nothing in reality is completely dry, right? So we have a equilibrium with the air, humidity of the air. Then it reaches certain equilibrium, the saturation level. So the material, the polymer is completely saturated. In this case, it's a very common, the most common epoxy polymer used in the market, the Digiba epoxy thermoset. And so we can see it can take up about 3.5% water. And we can model this very efficiently, usually use a Fickian law, so Fick's law, and typically for polymers it works quite well. There are some exceptions, of course, but Fick's law is usually the standard way. So let's take a look. If we have polymers of a dry state, then the saturated state with water, and then we want to see if we re-dry to the initial state, is there any change, for example, or does it, so is it the water content the only parameter that affects the property of a polymer, or something else is there? When we look into composites, so polymer composites also, it can be even more complicated that we have not a blue saturated line, but with time we can see that, for example, it can also drop. And I will explain why is that. Now, I mentioned that polymers can be different, and in terms of material-environment interactions, this is important because the hydrophobicity of plastics is let's say, the property that is interesting to us. And in some cases, polymers can uptake a lot of water and be swollen and can be affected by hydrolysis, such as nylons, polyamides and PLA. Although on the other case of the spectrum, for example, polypropylene or polyethylene, they are very hydrophobic, so they don't uptake a lot of water at all. Next, when we have water inside the material, it can cause the plasticization, and also it can be inside, let's say, inside between the polymer chains and starts to swell, so increasing volume. And in some cases, some polymers are affected also by chemical degradation, so hydrolysis chain scission. When the water is inside, it can also leach out the chemicals inside the plastic, and that is basically the water diffusion, but the diffusion out. So it's the same principle. We can use the same Fick's law, but with the other direction. And the degradation and all this plasticization, swell, and chain scission effects, they also affect the mechanical properties and of the material. So let's take a look again at this example of the most typical Digiba epoxy resin. For example, here we have in one of our papers, we identified the weak spots where the mechanism happens of the degradation of the epoxy network. So here's a bit of an explanation what happens. For example, there's cross-linking, which affects the glass transition temperature of the epoxy. And so when we redry the material to the initial state, we cannot regain all of the properties that we had before the aging, even if we have the same content of the water. Then also, as we know, very typically, this is important for in art conservation, for example. So epoxy is a glue and used in art also as a, let's say, to protect the piece of art. With time, this particular epoxy and most of epoxies, they age and they become more yellowish or grayish, so they change their color. And the reason for that in this case is a carbonyl formation. So the oxidation that happens even with quite low temperatures just in outside air. So it's not by sun, it's not photo-oxidation, this is thermal oxidation. So just kind of sum it up for this material, this is just an example for one material, but every material is different, as I mentioned. So it can be a lot of mechanisms: plasticization, hydrolytic scission, thermal oxidation, in this case, changing the color, leaching, thermal oxidative cross-linking. We can check all of that, let's say, with different methods as we go, so infrared analysis or so some spectroscopic methods. We can also test mechanically and see how the properties of a polymer, let's say in a dry, wet and redry state are changing, both statically and in fatigue. Then in terms of hygroscopic swelling, as I mentioned, so the water that is inside between the chains starts to swell the polymer. And this one is quite easily predictable, so we can use simple modeling tools for this one physically. It's almost like a thermal expansion, but it's just hydrothermal expansion. And this one can be done both analytically and with finite elements. With polymers, this is a linear correlation. For composite, it is orientation of the fiber dependent. But let's get to the more interesting part. So in this case, let's say how can we predict the property of a polymer if we don't have any testing facilities with us? So here we offer the QSPR methodology. So it's originally not ours. It's based on it's QSPR and QSAR. QSAR methodology is quantitative structure activity relationship. QSPR quantitative structure property relationships is something, is a method that has been developed mainly for drug discovery, so for medicinal pharmaceuticals. But it has been taken over also in the polymers and the material sector by DuPont. The idea is that we have any chemical structure, and we can use the mathematical graph theory to analyze the Lewis diagram. So the graph theory allows us to break down any structure into a number of parameters, in this case atomic and bond indices, so it's a 4-parameter. And with the mathematical operations we have, so these 4 parameters as simple valence and 0 and first order indices, structure, also called structural parameters. And the interesting part is that these parameters, they are unique for any chemical. So let's say if you have one polymer or another polymer, they will never be the same. So that's what gives it a fingerprint. And by using this combination of these 4 parameters, we are able to predict the properties by using an extensive data that is available to us. And now with the modern techniques, especially with the data science and machine learning and so on, this method has been given a new life in a way. So also another way to look into the prediction of properties of wet, for example, so saturated polymers, and also the effect of temperature, if we have the viscoelastic effect. So for example, we have a material creeping over time. The principle of time temperature superposition has been known for years. And it means that for polymers, for materials which have viscoelastic behavior, we can superimpose the effect of time and the effect of temperature. So they, let's say, creep at higher temperatures, they creep faster. However, what we have shown also that the effect of water present in the polymer can also be superimposed on that. So we have, for example, the blue is a dry master curve, the red is the wet, the saturated polymer master curve. And the interesting part is that these 2 master curves can be superimposed themselves by using, as we call it, dry to wet shift factor, which corresponds between the glass transition temperatures of the dry and saturated states. So if you are interested in this, for example, what can this do? Is that's the graph on the right, for example, in one paper that we wrote together with our colleagues in Hamburg, is that it allows you to predict how long a polymer will survive under given water content, temperature, and load, mechanical load. And you can use it as a surface basically to predict, let's say, at 20 megapascal, it will survive for this many years. At 40 megapascals, it will be less, and it will be this many years. So that's kind of how it can be useful. For some polymers, as I mentioned, for example, this epoxy that we looked at, it doesn't go hydrolysis. But there are many polymers that are used in our daily lives, such as polyamides, nylons, for example, or PLA, or one of the more common, let's say, first biopolymer in a way that is used a lot in 3D printing. They undergo hydrolysis with water, and it means that the reaction is typically non-reversible. So the properties can be lost over time until the material breaks down. So the hydrolysis can be predicted with such modeling ways, for example, the time-dependent decrease. However, let's look also in the case study, interestingly, to combine the QSPR methodology. So the way how we can predict the properties of a material from their chemical structure to further this approach into the aging. So this is something that has not been done before. We just published this last year. And this is basically the proposal that we had, in a sense that since the QSPR methodology can be used to link the chemical structure with their final properties, and we know, for example, how the hydrolysis happens, we know how the material will look as a structure, chemical structure after the hydrolysis has happened, and therefore we can put the parameters, the structural parameters of graph theory to the aged polymer and see how basically the end case looks like, the start case looks like, and then to using the chemical kinetics to get in between cases. So what this means. So, for example, for structural applications, we can have Young's modulus being predicted using the cohesive energy of this QSPR structural parameter via the QSPR structural parameters of a polymer, in this case PLA. We know that the mechanism is hydrolysis of ester bonds, and then we use infrared Fourier transform spectroscopy to measure the change in the intensity of the peak and to see the reduction over time. And then this FTR data we feed into the QSPR model, and then we obtain the predicted mechanical properties. So, for example, this is the kind of results that we obtained. So if FTR data with over time of aging of PLA in water is on the left, and then when we feed it to the QSPR, we're able to obtain the modulus. And this one was compared with the experimental, so it was validated. And the validation was looking something like that. On the left case, we have only aging. On the right case, on the right side, we have also recycling. So it was a little bit, we couldn't catch the effect of recycling with this, which was not that surprising because we have the hydrolysis model inside. And recycling is something in plus that. But let's say the QSPR was able to capture the decrease of modulus for pure aging. Now, if we take a look a little bit onto, let's say, the expansion of the aging of polymers inside the composite. Here, for example, we have a polymer composite aged for 9 months in 60 degrees water. And as we see, the mass keeps dropping. So what is happening there? I promise to come back to this one. So if we take a look at the same principles of, let's say, polymers and interface is mainly made up of a polymer itself, but different type, and also there's chemicals that bridge the fiber with the matrix. Typical interface composition is about 80% film formers, coupling agent about 10%, and the other chemicals for about 10%. The film formers are polymers, so it's about 80% polymer. And typically these sizings, they can also be degraded with time. It's also very small amounts, which is on the fibers. Therefore, it's really hard to measure experimentally, but we try to use a chemical engineering principle for the mass balance approach to get it. And if we look, let's say, how big is this interface? Is just barely less than a nanometer. So experimentally, it's very tough to look into this covalently bonded part. But also the one which is called the interface, right? So there's the difference between the interface being 2D and the interface being 3D. It's kind of like a mix of this film former together with the matrix. This can range up to 500 nanometers, but it's it's quite rough surface. So by knowing all of these processes that we have described, sub-processes for polymers, we can try to make mass balance approach. So if we have a gravimetric measurement and we know all the sub-processes that we have obtained, then the only parameter that we don't know is the dissolution of the interface, and therefore we can try to obtain that from estimate. That's not a very precise method, but still we can estimate the aging of interface. What happens is that, for example, we can see that the photographs, the micrographs of the composite and how it starts to degrade after a long time. So as I reminded you, at 9 months at 60 degrees water, and how the fiber matrix starts to debond and the cracks start also splitting along the fibers. So there's the interface which being filled in. So there's like a void being made. And if you see the dotted line, that is when the saturation with the Fick law is obtained. But what we interestingly see is that based on the composition of the fibers, and then you see the longitudinal and transversal fibers, the longitudinal, they start to increase in mass. So the water is being uptaken for 9 months. And for the C3, we saw that it keeps decreasing. So it's quite small, but from 0.96 to 0.87, but this is not statistically significant. And we found also a different source in literature by Peter Davies at Hydrothermal that they found a similar behavior. And what happens is that the whole composite, it keeps degrading, and they're like a pores, like voids that are becoming inside of it. And these pores are being filled with water with time. So it's not like it's chemically or physically bound, but it's just filling the voids. And therefore, we have this increase in volume. However, when this volume starts to connect together, they make a channel. And this channel can leach out this water outside, and we suddenly lose this mass. And this is for C3 composition for the short fiber for the transverse. It happens very quick. So we can see that we don't see an increase of weight uptake. And it straight goes to the degradation. So here, for example, data from Peter Davies is 10 years. So you can see that it's a composite which is in 60 degrees, for example, for 10 years straight in water. So it's a long process. And as I mentioned, temperature accelerates aging. So if we have 20 degrees water, for example, it's much slower process, but it's still the same mechanism. Interestingly, so I'm coming close to the conclusion already about, let's say, these various methodologies that we have inside this package. So with this with the mass balance approach that we looked at, we could obtain, as I mentioned, very rough estimate of this kinetic constant of the degradation of interface. And it has the same, so we have 3 scenarios because, as I told you, sizing is hard to analyze experimentally. So based on the models that are available in the literature, we had 3 scenarios. And in all 3 cases, so the scenario 1 is very improbable. That's maybe a little bit, yeah, I have to go into too much detail, maybe. Why is that? But the idea is that basically, so in short, is that it depends on the coverage of the sizing, how it is distributed, and also basically this profile of the fiber being aged with the water, being attacked by free water. So the first case is not very probable, so it's most likely scenario 2 and 3. But in any case, this gives us some boundaries of the, let's say, degradation time from 22 to 30 years of this typical composite at 60 degrees. And interestingly, that this kinetic constant that we estimated for the degradation of the interface is very similar to the degradation kinetic constant of glass fiber, which makes sense because it's silica or silica bonds that connect matrix and fiber. So to conclude, basically, I would say that we have proposed this modular approach, and I apologize, it's a lot of information that we tried to put together. It's many years of things that we tried to do. Basically, it's that we have a complex process broken down into smaller pieces. We try to attack each of them individually. And then we obtain this physical-based models for each constituent, and we try to, let's say, make a framework usable for as many different combinations as possible. So this framework was actually implemented in a marine composite standard by the NVGL, so the Noshke Veritas, and they use some of our models in the standard practice. So these quantitative models and methods, they can provide practical tools for the industry. And the main idea is that in our modern age, in a way, that we try to replace as much testing with modeling which we trust. Let's put this, that we can be confident with. So if we can be confident in the method, we want to replace the testing, because the testing for the industry means a lot of money. So for example, when they introduce a new composite material, it can take at least 1 to 2 years in a full testing house. So they book a testing house for a year, and it means millions of euros. For new companies to introduce new materials, it means that they have a bottleneck. They don't have this money to introduce new material. So even by substituting the rigorous physical testing by 20–30%, maybe we can cut the costs by 200–300,000 euros, for example. So this multi-scale approach then provides the means to analyze the environmental aging of composites. It can also be used, I didn't write it here, but it can be used for looking into the microplastics, right? So the microplastics being generated by the aging of polymers. We can use the physical modeling also approach to give a bit of the mechanistic look into this process. Yes, I would say that future work should include the improvement and the interconnectedness of these modules. And we still have some limited understanding of the interface, in my opinion. But this is, let's say, something that the whole composite material is working on. So thank you very much. Bye-bye. The point of the lens was some cursors on my side. Yes, maybe which we have three of us. You hope on the video with the speeder call. So the big ground more like so the PLA was it was basically in a consortium that was done about recycling of polymers. And it was in collaboration with the 3D printing. So they are very much interested in, let's say, the ABS versus PLA, the kind of typical old school polymers being printed. So PLA was chosen for this one, being the greener one of the two. Yeah. Okay. Yeah, I had some questions from my side. When you're testing these samples, how big are it? So it's nanometers and something like that? Yeah, so it depends which test, but let's say I have one picture here with the size that is for mechanical testing. So here we have a dog bone shape. This is something that we do for establishing the stress strain and the fatigue. Yeah, so that was pure polymer. With the composite samples, we usually do 3-point bending, so we don't strain them, typically a bit more complicated. We have how it's called, I-beams, for example. Yeah, profiles. And one more, this is water, just pure water, or it's some kind of salty water or yeah. So in this case, I didn't want to overcomplicate this pure water that we look. So the ionized water, yeah, basically like a distilled, pretty much. But also the effect of pH and the effect of salt, for example, it all affects the degradation for some cases. So it can affect the speed. In this case, we didn't look into that. However, more interestingly, it affects more the fibers than the polymers. So, for example, if we have glass fiber, then the aging of glass fiber will be very strongly affected by pH and salt movement. Yeah, probably usually going to Lipton industry and blades, which was glass fiber composites. So, and this is exactly what we're trying to find out how long we are degraded. Right, exactly. Yeah. So we want to know the lifetime and how long, let's say, how long is it safe, and we are confident that we can use the material, and also let's say we have to understand how does it degrade, right? If we want to be confident about it, not to have any surprises.
Yeah, and your slide was like 22, 13 years. It's exactly about composite materials.
Well, that was about interface, but if the interface fails, then the composite material will no longer be usable. But this is very much geometry related. So if you take a different geometry, it will change the number. So individually, we have to include this information, let's say maybe in finite elements to have the geometry.
But yeah, people who realize because like frozen water and melted water, so put their like a intensifier, let's say something.
Yes, so that typically here, the higher the temperature, the faster the reaction with Arrhenius approach. But if it is frozen, there's the freeze thaw. So if it goes around 0 degrees, it's another process which here it's not included, but it affects mechanically damaging the material. So if it is the ice that is being built inside them. Yeah. And currently, there's also research in the cryogenic aging of composites, especially interesting for aerospace. So they are looking very much into these freeze thaws and very low temperatures and also a little bit in the Arctic, like minus 40 degrees, for example. Around that, they look how does it, the brittleness, the aging, and so on, how it's affected. Actually, it could be very interesting for us to make exactly cryogenic systems because maybe astronomical telescopes use cryogenic cells, which are cooled down up to 20 gallons in the US, and how plastics will survive in salt? It's a good question. Yeah, so the typical problem, I would say, is the cycling. So it's not maybe the temperature itself, but it's the change of the temperature. So it's like, especially if it changes quickly from very low to higher and then again. So these cycles, that's the thermal shocks that are.
So it's mostly for ions, but still like something like.
I would say so, yeah. But still, also hydrogen, liquid hydrogen, the containers, that the vessels, the pressure vessels that are being. This is also a topic which is where this comes in.
Yeah, clearly. Thanks a lot.
Yeah, please ask.
Good question.
Yeah, sure.
I'm to this thing with this below. I didn't cover picture, but
no. To be honest, short answer is no. We haven't looked into tribal physics here, but it could be certainly for the surface. Like we were looking more into bulk, but I imagine that it could be like let's say some defects, right, that can be made on the surface, which can then start the crack, which can accelerate the process, for example. That can be, yeah.
Never about how we type of very to gravel, no, and both very fast, right? But what I want to like is so then I'm going to develop some good cut. What the first connection on what is not one but one device,
Right.
Like still for them. But it's a common stall on that. Out of plans that will include also the
Yeah, certainly it could be looked into it as well. I think here we kind of we're looking more into this bulk materials in a way that industry wants. They don't, kind of closer to the real life, not laboratory made material in a way that they want. What I mean by that is that, for example, industry, well, if it's not aerospace, which then they're very careful, but let's say it's something like a wind turbine. They just make it in one go, like the whole turbine or something like the whole chap. And so the process is not perfect in a sense, like it's not laboratory controlled, So we want to have this kind of real life relevance in a way. But I don't think they would check, for example, the tribal, like the whole surface, But it could be in the future, like with Aeronas, for example, that they have these robots going on the blades they could monitor maybe how the surfaces as well, like with the future functionality. It could be the case for the future, I think. Yeah.
Thank you again.
Yep.
Sure,
We can do that.
Thanks for the certificate.
Thank you.
Thank you for coming.
Thank you so much. Thank you.
And yeah, and please go to our next speaker. Not here. Just look at. Yeah.
Thank you.